I want to show you three proofs that either E equals mc squared or this other one that's sometimes known as the triangle proof, E squared equals mc squared plus pc squared. The first derivation I'm going to show you comes from minute physics, where Einstein apparently said cats equals mc squared. Now here's the key concept behind this proof, is that we've got a cat and it flashes, and as the observer we're going to do two operations that should result in the same observed energy. In the first circumstance, the cat flashes and then we accelerate. In this other circumstance, we accelerate and then the cat flashes. In both circumstances, our final end state is the same. The only difference between these two situations is whether we accelerated before the cat flashed or after the cat flashed, but we see the cat flash afterwards. Nothing happens to the cat, so it should be the same energy in either case that we are seeing at the end. There is an error in this video, though. It took me a while to figure out what this is, but this is the energy lost by the cat in the flash in its own reference frame, or if we're not moving relative to the cat. Now what this is supposed to be is the same flash observed while we're moving relative to the cat. Ordinarily we use this equation here for the relativistic Doppler effect, but this is not motion. This represents motion along the line of sight. What we should be looking for here is the transverse Doppler effect. The transverse Doppler effect causes the frequency of the light to be slowed down by a factor of 1 divided by gamma. Now 1 divided by gamma is 1 divided by 1 over the square root of 1 minus v over c quantity squared, which is simply square root of 1 minus v over c squared. Now if you use a Maclaurin series expansion of this thing, you will find that is approximately equal to 1 minus v squared over 2c squared. Notice we lost the square root sign and we've got a factor of 2 in there. But instead of showing you the Maclaurin series expansion right now, which I've done in another video, I am going to show you that the square root of 1 minus x squared is approximately equal to 1 minus x squared over 2 for small x. X, we'll call it x much less than 1. It doesn't have to be that much less than 1, you'll see. I'm going to use my TI-83 calculator here. Put the square root of 1 minus x squared in there for y1, and 1 minus x squared over 2 for y2. I'm going to graph it so that x goes from -1 to 1, and we'll have y min be 0 and y max be 3. And then just graph those two things and see what they look like. There's square root of 1 minus x squared, and there's 1 minus x squared over 2. And you can see in the region between about -0.5, -0.6 to +0.6, these are pretty close to the same thing. You'll see that the real 1 over gamma goes all the way to 0 at the speed of light, and goes all the way to 0 at negative speed of light and positive speed of light. This fake equation here, which is just an approximation, doesn't go to 0, so it's not an accurate representation, but for our purposes it's close enough. The point I want to make is that in his video he's got the positive sign here, and it should be negative. So I followed his proof down the line, and I'll fix each line as I go. There should be a negative sign here. This comes from the idea that the cat energy plus the cat flash energy should be the same under both circumstances. This negative sign should carry down to here. This is just from simplifying this thing above, and it probably ought to read, should put the kinetic energies on one side, so Ke2 minus Ke1, and then the positive version of E v squared over 2c squared on the other side. So now it's 1/2 mv squared minus 1/2 mv squared, and these velocities are going to be the same, because we accelerated by the same amount before the cat flash, or if we accelerated before the cat flash or we accelerated after the cat flash, a final kinetic energy of the cat should be the same. I'm sorry, the velocity of the cat should be the same. Kinetic energy of the cat is going to be oddly different. And since the velocities are the same, we account for it by putting in m2 in here and m1. Now we'll have, after we cancel out the 2's and the v squareds, we'll have m2 minus m1 equals E over c squared. That means delta m equals E over c squared, and so E equals delta m c squared. So the cat flash energy actually changed the mass of the cat. So this actually solves for the change in the mass of the cat that was a result of the flashing of the cat, the light lost by the cat. So that light has a mass. So I think it's a reasonably good proof. I just need to change that sign there and take into account that gamma factor is, and make sure that you realize that this is this is what they call the transverse Doppler effect, not an approaching or receding Doppler effect. Now the next proof that I'm going to show you that E equals mc squared comes from Mr. Boom Science. Now Mr. Boom Science lives in this strange world where the graphics behind him tend to move back and forth. But what Mr. Boom Science does, he actually, I think this is pretty close to Einstein's original proof. He takes a box of length L and mass m and a photon of energy E that emits from the left and goes to the right and embeds itself into the right side of the box. The box moves a tiny distance to the left while the photon moves a distance L to the right. So the photon moves L, the box moves delta x. So these are, it's a little bit of an approximation. Technically the photon's only going to move L minus delta x to the right, because the box will move a little bit. Now these are some assumptions about the setup. Immediately before emission, the photon energy is stored as a mass at the photon energy is stored as mass at position 0. It seems like kind of a big leap to make, but we're just assuming that the energy has mass over here on the left. And immediately after emission, or I should say immediately after absorption, the photon energy is stored here at position L as mass. And we make this assumption: the center of mass of the system is the same after absorption as it was before emission. Here's something that I guess some people find out that is well known, that the momentum of a photon, P equals E over C. It's also equal to H over lambda, or HF over C, but I'm not sure how all that works, but I guess that's those are well-known identities, so I'll go with that. The momentum of the box and the momentum of the photon are equal during this time, so when the photon takes off this way, the box will take off that way, and the momentums are going to be equal. Now, the center of mass before the transition is the same as the center of mass after the transition. So, x bar equals m times, okay, this is the mass times position plus the mass times the mass of the box times its position plus the mass of the photon times its position divided by the sum of the masses. And then after transition, we have the mass of the box times its position, or times its new position, because it's moved to the left by delta x, plus the mass of the photon times its new position, because it's moved across the length of the box, divided by the sum of the masses. Okay, so if you set these two things equal and simplify, everything cancels out and you can get this term here, m delta x equals ml. I leave that as an exercise. Calculate the amount of time that the photon travels across the box. That is just distance equals velocity times time, so that's how long. So that gives us a relationship between those three variables. The box velocity and its momentum is the velocity of the box is it's just delta x over delta t, and the momentum of the box is capital M times delta x over delta t. And so we've got the velocity of the photon is E over c, velocity of the momentum of the photon is E over c, the momentum of the box is m times delta x over delta t. Now, step 1, we set the momentums equal, so the E over c is equal to m delta x over delta t. And then using equation 4, which gave us c delta t, we replaced the delta t with L over c. So that delta t gets replaced with the L over c. And then we use equation 3, which, this one here, m delta x equals ml, and we solve that there, and this simplifies down, cancel out the L's and move the c over to the other side, and we get E equals mc squared. Now proof 3, I'm not actually even sure that this could constitute a proof, but I'm going to write this down. This is the total energy, this is PC, and this is mc squared. So usually this is just written E. So the formula is E squared equals PC quantity squared plus mc squared squared. And I don't know if this really constitutes a definition, but it's more of a it's not exactly a proof, it's more a couple of definitions. The total energy of a particle is gamma mc squared, which is, and I'll tell you, gamma is equal to the square root of 1 over the square root of 1 minus beta squared, where beta is V over C. So basically what I'm going to say here is gamma squared m squared c to the 4th equals, and then now the other thing that I'm going to say is P, momentum of a particle, is gamma m beta c. So this is also gamma mv. It's basically the relativistic momentum, which is mass times velocity divided by the square root of 1 minus beta squared. But anyway, I'm just going to write that in here. Gamma m beta c squared, because it's the c down here times the c up here, so that's squared, plus mc squared squared. Now if at this point we take out the m squared terms, which is right there, and right there, and the c to the 4th terms, which is right there, and right there, what are we left with? We're left with gamma squared equals gamma beta plus 1. Sorry, this is gamma squared beta squared. Gamma squared beta squared plus 1. I'm going to bring this gamma squared minus 1 over here. No, I don't want to do that. I want to solve for gamma, right? I'll take gamma squared minus gamma squared beta squared equals 1, which means factor out the gamma squared, we'll have 1 minus beta squared equals 1. And guess what? Gamma squared equals 1 over 1 minus beta squared, and gamma equals 1 over the square root of 1 minus beta squared. Now I could do that in reverse, basically by multiplying this by mc squared and this side by mc squared, and just go back the other direction until I ended up with apply these definitions backwards and this one backwards until I come back up to here, locate the energy momentum times speed of light as mc squared. Now when looking at this triangular, something I like to point out, if I draw kind of a circle, boom, like this, this part here, mc squared, that's the rest mass energy. Up here is, this whole thing is gamma mc squared. This part here is gamma minus 1 mc squared, is just the kinetic energy part. So if you just take that little strip right there, that's the kinetic energy, and this is the rest mass energy right here. However, there is a much better way of looking at this thing if you're willing to forsake geometry for hyperbolic geometry. Basically, this is the unit hyperbola, and imagine if this was time and this was space. The velocity of a line going up that way would be velocity is equal to, well, the side opposite, which is hyperbolic sinh of, well, let's call it the rapidity, divided by the hyperbolic cosine of the rapidity, which is also, which is the hyperbolic tangent of the rapidity, which is also equal to, the hyperbolic sinh is beta times gamma. The hyperbolic cosine is gamma, so this is just equal to beta. So that's not actually v. Let's see, this is v over c is what I did there. V over c is hyperbolic tangent and hyperbolic sinh over cosh. So I'm going to take this line, which is beta gamma, and this line, this line here, which is gamma, and this gamma is proportional. Well, if I multiply that by basically if I multiply that part by, so it's gamma mc squared, that's the total energy. The beta gamma mc squared is the momentum times the speed of light, and then this, what do I have here? This part here is the kinetic energy. The kinetic energy of the particle, however high that point is above that line, and then this part down here is the rest mass energy, mc squared. So one final issue that's kind of I was thinking about this morning. If I have, let's say, two particles, let's say this is the left edge of the box and this is the right edge of the box, and I'm putting this in a space-time diagram, so this is x going this way and this is time going this way. That means that over time neither edge of the box is moving. But I do something where I send a photon from one side to the other at the speed of light. Now, when this photon is emitted, that means this side of the box is going to be deflected off to the left, and this side of the box is going to be deflected off to the right. So what I'm finding interesting about this question is, if we consider this reference frame where they both appear to be moving, or both appear to be stationary at the beginning, then the center of mass is right here, up until this point in time, and then the center of mass begins drifting off to the left until this guy accelerates, and then I think that the center of mass is restored at that point because they both got the same velocity. So if the photon does not have mass, then the center of mass will actually move during that time and have a different location at the end than it did at the beginning. Now, some people say that the photon actually has gravitational mass, so during this process as it moves, it does not actually cause an issue with the center of mass moving